Good day, everyone. I'm Norman Wildberger. And today we're going to carry on with our course here in Math Foundations, where we're trying to orient mathematics in a more sensible and logical and careful fashion. We've been looking in the last few videos at foundations of analysis and issues relating to limits and ultimately to the weaknesses of the real number system, which are very serious weakness, having to do with the continuum and the basic structure on which calculus and analysis are based. Okay, so today we're going to be looking at extending the discussion in our last few videos to the idea of a limit of a sequence going to infinity. What does it mean for a sequence to go to infinity? Or to go to minus infinity, which is another possibility that we'll look at. Alright, so let me just remind you, since it has been a little while, of some of the things that we've been talking about in our last few videos. So one of the things that we've been doing is talking about the extended rational numbers, where we're augmenting the usual arithmetic with rational numbers with a new object which we could call infinity. And we did this in a certain way, basically by looking at pairs A, B of integers, or expressions A over B, but now without the usual restriction that B should be non-zero. So we'll leave that aside. And then we saw that we could create a viable arithmetic where we have some new objects appearing, in particular 1 over 0, which we denote by this symbol, this sort of lemniscate symbol, usually call it infinity. And we also saw that, well, to make this system kind of work logically and algebraically, we also needed to consider a new kind of object, 0 over 0, which I denoted by this asterisk. All right, so these are new kinds of symbols that are occurring in this extended rational numbers, which are not part of the usual rational number system. And I asked viewers to give me some suggestions for what we might call this new object 0 over 0. And I think the best suggestion was agreed to by quite a few people, that we should call it ZOZ. Okay? So this was a suggestion of TV10. And so thanks to him or her. And so we're going to call this new symbol ZOZ, short for 0 over 0. All right, so one of the interesting aspects of this new system is that it allows us to divide by 0. Okay, so it's interesting. Another interesting aspect is that the notion of equality becomes a little bit more complicated than for rational numbers. So the expression A over B equals the expression C over D, precisely when we can find non-zero integers m and n, so that m times A equals n times C, and m times B equals n times D. So this was one way of introducing infinity into our number system without having to actually resorting to believing in something supernatural or beyond our capabilities. All right. So it's not that I'm suddenly believing in infinite sets, because I don't believe in infinite sets, and neither should you. But nevertheless, here is a very finite, precise way of introducing something which we might call infinity into our arithmetic. So this is certainly one very interesting aspect, or one way of thinking about infinity. Another topic that we discussed is the idea of a particular kind of sequence. And in my opinion, the word sequence, just like the word function or the word number, is really a meta-mathematical term. It's not very easy to define precisely what it means in a mathematical sense. It's easy enough to give some examples of things that we might like to be sequences or functions or numbers, but to actually draw a clear fence around the concept that separates the concept from things which should not be included is very challenging. And since nobody seems to be able to do that, I prefer to not work with those words in the usual generality. So in my opinion, it's much safer to sort of follow the computer scientists and try to have more constrained or limited usages of words. In particular, I'm quite happy for us to build up the idea of a sequence, sort of slowly, one step at a time, by starting with simple-minded kinds of sequences that we can really nail down, and then maybe a little bit more sophisticated ones, and then a little bit more sophisticated ones after that. And we can leave it sort of as an open-ended kind of thing. We don't have to embrace the whole concept all at once. In fact, I think it's probably dangerous to aspire to that. All right. So our approach, for example, to discussing sequences is to restrict ourselves so that we know exactly what we're talking about, that we can all agree. And the kinds of sequences that we are considering are the ones that are essentially given by rational functions, what I prefer to call polynumbers. Okay, it's like a polynomial divided by a polynomial. 1 plus alpha squared over 2 plus 3 alpha squared. So that's a polynumber. It's a rational polynumber. And associated to that, we can create a sequence. Well, it's a sequence which I prefer to write as an on sequence, so it's an ongoing sequence. It's not a finite sequence. It's something that keeps on going. And the way we generate it is by thinking about this particular expression, a bracket, then p of n, where p is this, and then a pointy bracket. Okay. And we can think about this thing as being evaluated at k equals 1 or k equals 2 and so on. If we plug in n equals 1, then we get 2 over 5. Plug alpha equals 1 here, we get 2 in the numerator and 5 in the denominator. If we plug alpha or n equal 2, then we get 5 over 14. So by substituting successive natural numbers, we can get a sequence of numbers, rational numbers. And we can think about this particular sequence as being generated by this polynumber. In other words, we don't really have to actually think about the sequence itself, because the polynumber itself is already a completely finite prescription of what we think about as the sequence. So there's a distinction here between what we can write down very concretely, namely this expression here, and what we can associate to it in our minds. Namely, we can think about associating to it this sequence which keeps on going and going. But ultimately, it's not important for us to capture this sequence because we can work just with the expression. As you know, I'm very expression-oriented, and this is a way of cutting out all this chat and discussion and philosophizing, just by concentrating about what we can actually write down and making sure that we have a consistent and logical approach to the things that we write down. All right, so this is a rational polynumber on sequence. And officially, it's this expression. So this is actually the rational polynumber on sequence. But if we want to, we can evaluate it at 2 and get 5 over 14 if we want. All right, so this is a narrow but useful kind of sequence which allows us to avoid giving a precise definition of the term sequence in general. All right, so we're restricting ourselves to just this narrow kind of sequence. All right, and then the next thing that we did is we talked about limits of rational polynumber on sequences. So if we have such a rational polynumber on sequence, and if A is a rational number, we wanted to define what this expression means. What it means for the limit as n goes to infinity of p of n equals A. What does that mean? So what does it mean for the sequence to have the limit 17? Or minus 3/2, etc. Well, here's our definition. And it's a novel definition because it's a simpler kind of concept of what a limit is. In fact, it's appreciably simpler than the usual one. All right, so we say that this occurs precisely when we can find two natural numbers, k and m, such that if n is a natural number which is bigger than or equal to m, then these two inequalities are satisfied. The difference between p of n and a is sandwiched between minus k over n and k over n. So that's supposed to be true for all n bigger than or equal to this starting value m. All right, so we called m the start, and we called k the scale. So for example, the limit of 1 plus n squared over 2 plus 3n squared as n goes to infinity is 1/3. Let's check why that is true. So in order to establish this, we need to basically check that this condition is satisfied. So ultimately it comes down to finding two numbers, k and m, and showing you exactly what they are. They have to be natural numbers, like 5 and 349. Most of the time they're not that complicated. They're usually like 1 or maybe 2, but sometimes we have to use some more complicated numbers. But generally they're pretty simple, at least for these simple kinds of examples. Okay, so what do we have to do? We have to look at the difference between the polynumber and the limit. So here's 1 plus n squared over 2 plus 3n squared minus 1/3, and then we're going to rewrite this. Take over the common denominator, and then we get 3 times 1 plus n squared minus 2 plus 3n squared. And the 3n squared appearing here and the minus 3n squared appearing there will cancel. And we'll just have 3 minus 2 for a total of 1. So this quantity here simplifies to this. Alright, so what do we want to do? We want to find k and m so that this quantity is sandwiched between minus k over n and k over n. Okay, so now we observe that this quantity here is sandwiched between minus 1 over n and 1 over n, if n is bigger than or equal to 1. Let's see why that's the case. So if n is bigger than or equal to 1, it's a natural number like 1 or 2 or 3, then it's obvious that this inequality is satisfied because this is a negative number and this is a positive number. So yes, this will automatically be bigger than that, no problem. Why will this be less than or equal to this? Well, this is equivalent to saying that the n is less than this. Okay, but it's kind of obvious, I think, that if n is a natural number starting with 1, that if you take n and you square it, multiply it by 3, add 2 and multiply by 3, you're getting something that's bigger than or equal to the number you started with. Okay, so squaring a number makes it at least as big. Multiplying it by 3 makes it bigger, adding 2 makes it bigger, multiplying by 3 makes it bigger again. So the denominator here is bigger than the denominator here, so automatically this entire fraction is less than or equal to this entire fraction. So this is a true statement for all n bigger than or equal to 1. So in this case, the k and the m that work are k equals 1. The numbers that are here in the numerator just is k equals 1. And the range of values of n for which this works start with m equals 1. So m is the start. So we've exhibited k equals 1, we've exhibited m equals 1, and we've convinced you, hopefully, that if n is bigger than or equal to this m, then this inequality will be true. And that proves to us that the limit of this actually equals this. And geometrically, what's going on is that the difference between this thing and this thing is getting smaller and smaller as n gets bigger, because it's sandwiched between these two things, and they're both getting closer and closer to 0. Once n is 1,000, then this and this are just a little bit less and a little bit more than 0. And as n gets bigger and bigger, they zero in or home in on 0. So the difference between these two things becomes smaller and smaller and smaller, closer and closer to 0. That's our intuitive meaning of what the limit means. All right, I want to show you a picture of the kind of content of that limiting definition. This is a picture I've shown you before. But before I do that, I just want to make the note that we are using this infinity symbol in now a couple of different ways. So we use the infinity symbol in the extended rational numbers. It's a particular algebraic object that we concocted. And we're also using it in this expression. It's just sort of part of the definition. It's meant to imply the idea that the number n is getting bigger and bigger. That's really the only content of it. But nevertheless, we are using the same symbol that we were using there. And so we should note that these two symbols here are playing different roles. Now that's maybe not the best situation, but it's something that we do quite a lot in mathematics, especially when it comes to numbers. The number 0, for example, or the number 1, end up occurring in lots of different places where they often play the same kind of role, but technically speaking, the number 1 as a natural number is different from the number 1 as a rational number, different from 1 as a polynumber. But we often use the same symbol because it might get a little bit onerous for us to always be adjusting our symbol depending on the domain we're in. But maybe, strictly speaking, we should do that. Okay? And if there's any possibility of confusion, we should probably definitely do that. But anyway, I want to at least point out the fact that we may be using this concept of infinity in a couple of slightly different ways. All right, and here's that picture that I wanted you to make sure you understood. So what does it mean for the limit of a sequence p of n as n goes to infinity to be equal to a number a? So here's the sequence's values. So p of n is maybe, I don't know, minus 2, and here p of 2 is maybe 1, and p of 3 is maybe 4, and maybe 3 point something. And here are the various values of p of n, marching up and down as we're going in that direction as n gets larger. And this is supposed to illustrate the idea that this sequence is somehow getting closer and closer in terms of its values to this rational number a, whatever it is. And the meaning of the inequalities are that we have these two essentially hyperbolic branches that are converging to a. So there's a minus k over n, that's sort of that lower branch, and a plus k on n, which is that top branch. And k is some scale factor that, well, if we adjust it, it means that this hyperbola, gets a little bit further away or a little bit closer to the limiting line. It just scales it. But the crucial dependence is on n. Here is n. As n is going in this direction, a minus k over n is approaching a from the bottom, and a plus k over n is approaching a from the top. And we're supposing that p of n is sandwiched between these two after some point. It may not be sandwiched between these two for all values of n. We just require that at some point, given by our starting value m, after that point, then p of n does behave and stays within the two sort of hyperbolic branches. That's the picture I want you to have in mind in terms of a limit of these rational polynumber on sequences. So what I'd like to do today is to extend our definition and our understanding of limit to the idea of the limit of a sequence being positive infinity or the limit of a sequence being negative infinity. I want to define what that means. All right, so we want to define two more kinds of behavior for a rational polynumber on sequence in terms of limiting behavior as the n gets large. Okay, and the examples that illustrate what we want to have happen are these. So the limit of the sequence n squared. That's the sequence 1, 4, 9, 16, and so on. As n gets bigger and bigger, the square gets bigger and bigger, and it gets bigger without any limit. So we're going to want that the limit of n squared as n goes to infinity is infinity. And we'll write plus infinity or positive infinity here. We're going to do that to distinguish it from minus infinity, and also to help us distinguish this infinity from the infinity that occurred in the extended rational numbers, which doesn't have a sign, and which treats plus infinity and minus infinity as the same, essentially. So it's a different kind of use of infinity. Related, but somewhat different. Another example, 1 plus n cubed over 2 plus n. Now as n gets big, well, 1 plus n cubed is going to get big. But so is 2 plus n. They're both going to get big. But the quotient is going to get big because n cubed, sort of the dominant term here, is much bigger than n once n gets large. So we do expect that the limit of this should also be plus infinity. And here we have the limit of 2 minus n to the fourth over 1 plus n minus n squared. Okay, so the way we think about this is that for n very, very large, basically the minus n to the fourth term in the numerator dominates, and the minus n squared term in the denominator dominates. So basically this is sort of like minus n to the fourth over minus n squared, which is a lot like n squared. So it really behaves a little bit like this one, and its limit should be plus infinity. Examples of when we have a limit going to minus infinity. Here will be 1 plus n squared over 3 minus 4n. If you plug in a very big value of n, like n is 1,000,000, then this number is a very large negative number. It's not a big positive number, it's a big negative number. Similarly, n cubed over minus n squared. The n cubed dominates the n squared, so it's big, but there's a minus sign floating around here, so we're actually going to go down to minus infinity. And here again there's a minus sign, and the numerator is an n to the 8, and here we have 100 plus 99 n to the 5th. These are a little bit big numbers, but the n to the 8th dominates this denominator, so the result is that the thing is going to go to infinity, but going to go to negative infinity because of that minus sign. And you can see that by imagining what you get when you plug in n equals 1,000 or 1,000,000 or some biggish number. Then you're going to see that this is going to be a large negative number. So what we want to do is we want to define what these things mean. We have an intuitive idea of what it should mean. Now we want to say it so precisely and clearly that everybody can use this terminology without any misunderstandings or ambiguities. Right? That's our aim. All right, so let's have a look at our definition. If P of n is a rational polynumber on sequence, then this, namely the limit as n goes to infinity of P of n equals plus infinity, that means the following. It means that we can find k and m natural numbers, that's just as before, such that if n is bigger than or equal to m, that's just as before, then this inequality holds, that n over k is less than or equal to p of n. Or in other words, that p of n is bigger than or equal to this multiple of n divided by k. That sort of makes sense, I hope, that if P of n is in fact bigger than n over k, maybe k is 12. So if we can prove that P of n is bigger than or equal to n over 12, at least once n gets to a certain point, then n over 12 is going to go up and up and up as n gets large. And if P of n is bigger than n over 12, well, then P of n will also have to go up. And so it deserves to be going to plus infinity. All right, and what about the definition, the limit as n goes to infinity of P of n equals minus infinity? That means we can find k and m natural numbers, so that if n is bigger than or equal to m, then now P of n is less than or equal to minus n over k. Again, it's n divided by some natural number, maybe like 12. But we have a minus sign here. So what would it be if, say, p of n is less than or equal to minus n over 12? Well, as n gets big, minus n over 12 is going to get big in a negative way. It's going to become a large negative number. And if p of n is less than or equal to that large negative number, it means that it's also a large negative number. So as this goes down, down, down in size, more and more negative, well, this is also going to be forced to go down in size. So this is going to be heading off towards minus infinity. So this deserves to be also called, so it makes sense to say that this is also heading to minus infinity. And I just point out again that these terms, plus infinity and minus infinity, that are on the right-hand side here, are different usages from the infinity that we defined when we were talking about the extended rational numbers. It's a different kind of meaning. And I'm hoping that this plus sign and the minus sign that we put in front of things make it more clear that that's the case. Let's have a look at some examples. We're kind of moving in the direction of analysis here. So the arguments that I'm going to present here are relatively simple kinds of arguments that one does in an introductory analysis course. So for those of you who haven't taken that, maybe it's been a while since you've taken calculus, don't worry too much if the details maybe are a little bit complicated or maybe a little bit unfamiliar. We're not going to be going too far in this direction. I just want to show you sort of how the story goes, and that if you worked at it, you could completely master this relatively simple-minded way of thinking about limits. Okay, so an example. Here we have a situation where we have a limit going to plus infinity. The limit of 1 plus n cubed over 2 plus n equals plus infinity. Let's explain why that is. All right, so the kind of inequality that we want to establish is that this thing here is bigger than or equal to n over k for some appropriately chosen k and for all n past some point m. So this is the kind of inequality that we have to establish. So let's just look at this inequality. And we're going to observe that this thing is equivalent to this. So how did I go from here to here? Well, I multiplied both sides by 2 plus n. Okay. Now when you have an inequality, you multiply both sides by something, you have to make sure that what you're multiplying by is positive, otherwise the inequality will change. But if n is a natural number, which is the domain in which we're considering things, then 2 plus n is always positive, and so multiplying both sides by 2 plus n is not going to change this inequality. Okay. Then we're going to get 2 plus n times n, or 2n plus n squared over k. And we're going to want to establish that this is less than or equal to 1 plus n cubed for all n bigger than or equal to something. So we have to ask, well, what k can we choose? Well, we have some freedom here, and in fact it works if we just let k equals 1. So let's suppose that k equals 1. Then this becomes the inequality. 0 is less than or equal to 1 minus 2n minus n squared plus n cubed. So if k is equal to 1, then I'm rewriting this inequality by bringing everything to the right-hand side. So basically I have to prove that this is always positive. And we wanted to prove that it's always positive for n past some point. Okay. We don't require that it's true for all n, but just that there's some m, so that once we're past m, then it's true. Alright, so I claim this is valid when n is bigger than or equal to 2. This is the case when m is equal to 2. How can we see that this quantity is bigger than or equal to 0 when n is bigger than or equal to 2? Well, one way, if you know a little bit about graphing polynomials, okay, this is a cubic polynomial, polynumber. We can graph it, at least approximately. And I hope this is somewhat familiar, right? It's a cubic kind of polynumber, so it has that kind of shape. And we can see that, well, eventually it gets positive. And looking at the graph, when n is bigger than or equal to 2, then yes, indeed, the value of the polynumber is bigger than or equal to 0. It's not bigger than or equal to 0, for example, at 1. If you plug n equals 1, you get 1 minus 2 minus 1 plus 1. That's minus 1. It's not true when n is 1. But it is true when n is 2. For example, if you plug 2 in, you get 1 minus 4 plus 8, which is positive. And we can claim that this is going to be true for all n bigger than or equal to 2. So one way of seeing this algebraically is to look at this and rewrite it in this way. To write it as n squared minus 2 times n minus 1. And I got that by taking the n squared times n, that gives us an n cubed. I also want a minus n squared, so I'm going to put a minus 1 here, that'll give us a minus n squared. And I want minus 2n, so I'll put a minus 2 here, that'll give us minus 2n. And altogether then what's left over I have to have 1. So right now I have plus 2, so if I subtract 1, then it's all balanced. If we write it this way, then we can see that if n is bigger than or equal to 2, then this is going to be bigger than or equal to 1. And this is going to be bigger than or equal to 4 minus 2, which is 2. So in all of these cases, this is bigger than or equal to 2 times 1 minus 1, which is 1. So it's bigger than or equal to 0. So one way or the other, we convince ourselves that yes, this inequality is true if n is bigger than or equal to 2 and if k is equal to 1. So if k equals 1 and m equals 2, then n bigger than or equal to 2 implies that this basic inequality is satisfied, and so the limit of this thing really is positive infinity. So at the end of this calculation, I can give you these certificates. I can say, here is k, it's equal to 1. Have a look right there. And here's m equals 2. Here it is right there. I'm showing you these two numbers, and these two numbers are certificates for the inequality that we want to establish. It's a finite process. That's the critical thing. We only have to do a finite amount of stuff. That's good because we're not capable of doing an infinite amount of stuff. At least I'm not. All right, so here's an example. Limit as n goes to infinity of 1 plus n squared over 3 minus 4n. Claim that's equal to minus infinity. Okay, so what do we have to observe? All right, so how do we establish that? Here is the basic inequality from the definition. We have to show that this thing here is less than or equal to minus n over k for some k, a natural number, and once n gets past some point m, also a natural number. So this should be true for all n past m, and you get to choose where you want to start. So let's simplify this first by, say, multiplying by this 3 minus 4n, which is in the denominator here. So I multiply that over here, and I get minus 3n plus 4n squared there over k. But notice that this less than or equal sign has changed to a greater than or equal sign. Why is that? Well, because the thing that I've multiplied by is in fact going to be negative. Because the n's that I'm considering are all bigger than or equal to 1. If n is bigger than or equal to 1, then 3 minus 4n is necessarily negative. So when we're multiplying by that negative quantity, the inequality sign has to change. That's why there's a greater than or equal to sign there, not a less than or equal to. Okay, so now we have to choose a value of k so that we can establish this inequality for some reasonable range of n's starting somewhere. One convenient thing to do is to set k equals 4, because then there will be cancellation with this 4 here. And then this n squared here will cancel with that n squared there. Things will become a lot simpler. So if k equals 4, then this inequality becomes just 1 is greater than or equal to minus 3n over 4. When is this thing valid? Well, this is valid whenever n is bigger than or equal to 1, because there's a negative sign here. N is a natural number bigger than or equal to 1, then minus 3n over 4 is going to be certainly less than or equal to 1. Conclusion, if we choose k equals 4 and m equals 1, then if little n is bigger than or equal to m, then this basic inequality is satisfied, which proves to us that the limit is minus infinity. And again, I have certificates. The certificates here are the scale is k equals 4, and the starting point is m equals 1. I can show you those, that I've done the right work, and then you can check the inequality is true. All right, very good. There's a whole bunch of other things we could do now if we were sort of doing an analysis course, but we're not doing that. We're just interested in investigating the foundations and getting enough understanding of what a limit is in order to be able to understand some of the difficulties with the current theory of real numbers. And then once we get to some other aspects of analysis, this will come back, be a good help for us as well. So in our next video, we're going to have a look at the standard usage of the word limit. In modern age, it's usually considered a great accomplishment that the late 19th century mathematicians had a so-called rigorous understanding of the limit process. And the usual story is that Weierstrass and Cauchy and so on ascended to a much greater height than Euler and Newton ever had because of this all-important definition. This is a story that I would like to differ with. Okay? In my opinion, the standard definition of a limit that you find in all calculus and analysis texts is in fact logically very weak. It's logically problematic. And in our next video, I'm going to explain to you exactly why. So it's going to be another video that's going to be a little bit difficult for students who are being trained in the current system to deal with. But you can have a scientific approach and see whether I'm actually right and whether you will agree with me. It'll be very interesting. So I hope you'll join me for that. I'm Norman Wahlberger. Thanks for listening.